Welcome to This Explainer. You know, when we think about this huge AI boom we're right in the middle of, our minds immediately jump to those massive, powerful GPUs, gigantic data centers, and the almost magic capabilities of large language models. But there's actually a hidden bottleneck in all of this that almost no one is talking about. And it literally sits right at the foundation, our data infrastructure. The very file formats we rely on to store all this information, they're getting pushed to their absolute breaking point.
Which brings us to a pretty critical question. Are old files actually slowing AI down? Well, the short answer is absolutely, yes. We're right in the middle of a massive paradigm shift here. AI models are just racing ahead at breakneck speeds, processing crazy amounts of multimodal data and these really complex vector embeddings. But the legacy file formats trying to store all this, they are structurally stuck in the past. To figure out how we fix this whole shebang, we first need to understand exactly why these old methods are collapsing under the sheer weight of modern machine learning.
Okay, let's dive right into this. Section 1. The AI data bottleneck and why legacy formats fail.
So, for years, the undisputed king of the data lake era was a format called Apache Parquet. And hey, it was fantastic for what it was built to do. It was heavily optimized for something called batch scanning. Basically, if you needed to read an entire column of data just to find an average or a sum, Parquet was your absolute best friend. But modern AI just doesn't work like that. Things like AI training, especially random batch sampling, and modern vector search demand instant random point access. These AI models need to grab very specific scattered data points immediately rather than sluggishly sweeping through entire columns.
To put it simply, getting just a single specific row of data out of Parquet is incredibly frustrating for an AI model. Why? Because in Parquet, reading a single row actually forces the system to decompress an entire row group. It's literally like having to unpack your entire overstuffed suitcase just to find your toothbrush. You're doing all this heavy lifting, decompressing all this surrounding data, just to grab the one tiny piece of information your model actually needed right then. It is hugely inefficient for AI. So how do we fix the suitcase problem? Well, we build better suitcases. The new generation of AI-native formats, like one called Lance, completely overcomes this roadblock. By totally redesigning how the data is structured specifically for these modern workloads, Lance delivers 100 to 1,000 times faster random access than Parquet. And it does this while still keeping all those great benefits of a columnar layout. Think about that for a second. 1,000 times faster. That's not just some incremental update. That is a staggering leap in performance that fundamentally changes how fast we can train and query these models. But here's the crucial point. Random access is really just the tip of the iceberg here. Modern AI relies heavily on really wide feature tables and vector embeddings. You know, those giant arrays packed with thousands of floating point numbers. Older formats use these heavy metadata frameworks that simply choke and slow down query parsing when dealing with those high dimensions. On top of that, they rely heavily on traditional CPU-based decoding, which creates a massive bottleneck. And historically, because you couldn't store these complex embeddings efficiently, data engineers basically had to store the raw data in Parquet, but then index those embeddings completely separately in a standalone vector database. Talk about adding massive complexity and headache to your data pipeline. That brings us to Section 2, enter the AI-native file formats.
Now, what's really exciting is that we're witnessing the emergence of a brand new generation of columnar file formats. These are engineered from the absolute ground up for large language models, deep learning, and complex vector search. Let's look at Lance again as our first example. Lance is totally built for multimodal AI. It doesn't just handle text, it seamlessly handles your image, audio, and video datasets. But its absolute superpower? It supports native vector indexes, things like IVFPQ and HNSW, right inside the file structure itself. Remember that complex standalone vector database we just talked about? You don't need it anymore. The index and the data live together on disk, perfectly unified. It's a real game changer.
But what happens when we need to scale this up to, say, planetary scale? Well, meet Nimble. This one was developed by Meta. Meta was dealing with these extreme-scale machine learning feature tables that literally had tens of thousands of columns. Standard metadata frameworks would just instantly crash or completely bog down under that kind of weight. Nimble actually solves this by using an ultra-lightweight metadata structure based on flat buffers. It uses this zero-copy layout to completely eliminate those metadata bottlenecks during their massive training runs. And third, we have Vortex. Now, Vortex takes a slightly different, highly optimized angle. It's an extensible columnar format that zeroes right in on high-performance vector and analytical queries.
How does it do it? Basically by speaking the native language of modern hardware. Vortex leverages SIMD CPU instructions and direct GPU memory loading. By combining adaptive encodings and zero-copy memory mapping, Vortex essentially just bypasses all those traditional bottlenecks and eliminates CPU decoding overhead entirely during model training. It feeds the hardware exactly what it wants, exactly as fast as possible.
And you know what's really amazing? Across all these new formats, there's a shared capability that is an absolute lifesaver for data engineers: zero-copy schema evolution. Back in the old days, if you wanted to add new vector embeddings or maybe some tags to a massive dataset, you often had to literally rewrite the existing data. It was painful, it was incredibly expensive, and it took forever. But these new AI formats, they allow you to evolve your schema and add new information without having to rewrite any of the underlying data. It is just beautifully efficient.
Let's wrap things up with Section 3, the open source ecosystem.
As we look at how these technologies are actually being shared with the world, it is honestly incredible to see that this crucial infrastructure isn't being locked away in some proprietary corporate vault. Nope, nearly all of these powerful modern analytics formats operate as open source projects under open licenses, like Apache 2.0. This evolution table here perfectly illustrates the generational shift we've been talking about. If you look down at the bottom, starting with basic text formats like CSV, we eventually evolved to rapid streaming with binary row formats like Avro. Then we revolutionized SQL analytics with Parquet. But look at the very top today, we see our AI-native formats, Nimble, Vortex, and Lance. They're entirely open source, and they're pushing the absolute boundaries of what's possible for multimodal AI feature tables and real-time query engines. It's just a stunning evolution of how our data storage is racing to keep pace with our computational needs.
Which leaves us with this final, pretty fascinating thought. We've gone from simple text logs all the way up to GPU-accelerated, multimodal columnar files with built-in vector indexes, all just to keep up with today's models. But artificial intelligence isn't stopping here. As AI continues to evolve, as these models become capable of continuous, real-time reasoning across entirely new modalities, what is our data going to look like next? The truth is, this infrastructure revolution is really just beginning, and the file formats of tomorrow are probably being drafted right this second. Stay curious, keep exploring, and thank you so much for joining me on this explainer.